In a time before time was hashable, I made a controversial claim, and programmers have no idea how to do mathematics. Given my enormous fame, many would say that I have a responsibility to own up to the defamation I spew. I'm sure the programmers will be okay. This slight on them is probably as significant as the difference between 0.1 plus 0.2 and 0.3. However, if you're one of the affected programmers, hang tight, and apologies coming by the end of the video. On the surface level, real numbers are pretty intuitive. A real number is just an integer plus an infinite sequence of digits after the decimal. However, our intuition sucks. This is why mathematicians bother with proofs. Specifically, it's really hard for us to discern between really big finite and infinite. Deep down, we're all inherently ultra-finitists, no matter how hard we try. You might object that you don't have this difficulty, and maybe you're right, and I'm just stupid. But intuition breaks down pretty quickly when we run out of finite handles on things. Mathematics puts us in a pretty rough spot. We want to talk about infinite things, but we only have finite tools. Things we talk about need finite representations, and proofs have finite length. On the other hand, I just said that a real number has a possibly arbitrary infinite sequence of digits after the decimal point. In particular, the digits of a real number may not have a pattern or a rule to generate subsequent digits. I know this. It's like pi, right?
Contained within this string of decimals is your birth date, combination to your locker, your social security number. It's all in there somewhere.
First of all, the normality of pi, which would make this video true, is an open problem. Secondly, pi does admit finite representations, like this. Or, if you want to read off hex digits, this. So real numbers can have infinite information. Big deal, I hear you say. After the 10th digit, we can't even tell numbers apart. You say that, but precision you need is obviously context dependent. You may say that 1 and 1.0000000000001 and 0.99999999999 are pretty indistinguishable, differing by 10 to the minus 11. But my definitely not contrived and completely natural monomial function f of x equals x to the 10 trillion begs to differ. F of 1 is 1, but nudging up by 1 10 to the 11th takes you to about 26.88 tredecillion, and nudging down by 1 10 to the 11th takes you to about 37.2 quattordecillionths. Okay, fine. My example is pretty contrived. I can't help it. I'm a pure mathematician. All of my examples are contrived. Who do you think comes up with the elementary school problems where James buys 160 identical spherical 50 centimeter wide watermelons, travels 3 kilometers west and 4 kilometers north to get to her hemispherical igloo with a radius of 10 meters, and then asks if she can fit all of those watermelons at home, assuming that each watermelon gains 1 milliliter of volume per meter traveled from absorbing snowfall? In any case, the average person's working understanding of real numbers relies crucially on the assumption that we can work with suitably accurate approximations of real numbers in our day-to-day lives. This is why most people seem perfectly content with floating point numbers despite their interesting artifacts. I know some of you are programmers still waiting for that apology I promised. While you wait, consider this technical interview question. You are building a numerical math library for some wealthy clients, but they need better precision than is offered by long doubles. Runtime and memory are no issue, they say, but our application requires arbitrary precision. Arbitrary precision means that you can man-kiss the floating point model goodbye. So what will you do? Maybe the most natural way of implementing as precise as needed real numbers is to encode them as a pair, consisting of the integer part of the number and a generator which yields as many of the bits of the fractional part as you would ever want. This meets the arbitrary precision requirement, so this looks golden. However, how would you implement addition of real numbers in this model? If we're given two real numbers generated digit by digit, there is a subtlety that makes generating the sum digit by digit difficult. Propagating carries might occur well below your digit of interest, so it may take generating arbitrarily many digits before you can even get the integer part of the sum correct. Addition is a pretty important thing to get right, and probably also important to keep simple, so this complication won't fly. Runtime may be no issue, but we can't have an addition algorithm that might take infinite time to get finite precision. Luckily, memory is no issue. The idea behind spitting out the fractional part of a real number bit by bit is to give a sequence of finite approximations of the real number. So why don't we just allow all real numbers to be encoded as a sequence of finite approximations? We can even control the accuracy of the sequence. For example, we can force the nth term of the sequence to be accurate to an error of up to 1 over 2 to the n. With this model of real numbers, we can define addition with ease. As an application, let's use our implementation to compute the square root of 2. Since we know that the square root of 2 lies between 1 and 2, we can use a binary search. Briefly, we update the lower or upper bound to the midpoint depending on whether the midpoint squares to something larger than 2 or less than 2, and we repeat this process until we can get the bounds within the precision we want. The same idea can be used to calculate the square root of any non-negative rational number. Now that we can calculate the square root of any rational number, we can extend this to calculate the square root of any real number. For simplicity, assume that x is greater than or equal to 1. In this case, if xn is within epsilon of x, then square root of xn is within epsilon of square root x. Therefore, we can piggyback off of our square root function for rationals to get a square root function for reals. To calculate square root of x within 1 over 2 to the n, we take a 1 over 2 to the n plus 1 approximation of the square root of the rational number xn plus 1. This is a general pattern. If we want to define a function f from R to R, we can start by defining the function on rational numbers, and then use f of xn for suitably large n to approximate f of x. However, this pattern only works if f of x is continuous. We used a binary search to approximate square roots of rational numbers, so a natural question you might have is why we didn't also use a binary search for the rest of the real numbers. Well, the problem is right here. While most arithmetic can be implemented using our model of real numbers, we can't implement any of the comparison operations. Specifically, how would you implement the function isPos, which just checks if a number is positive? You might think, well, x is positive if and only if there exists some n sufficiently large such that xn is greater than 1 over 2 to the n. Since xn is within 1 over 2 to the n of the true value x, being greater than 1 over 2 to the n means that x itself is greater than 0. Therefore, perhaps I can implement the function isPos as follows. Although this implementation is well behaved for all positive and negative x, the function runs forever if we plug in the numbers 0. Basically, if the function is still running after n iterations of the loop, we aren't able to tell whether the input x is 0 or if x is some real number that is really close to 0, as in within 1 over 2 to the n plus 1. We encounter a very similar problem if we try to represent real numbers as a sequence of bits. This reflects the surprising fact about constructive mathematics.
Nope.
This fact is often paraded in a much more provocative way, claiming that all functions from R to R are continuous. But this is just media hyperbole. The truth is that constructive mathematics cannot prove the existence of discontinuous functions from R to R, as this would require constructing such a function. The source of the problem in defining a discontinuous function lies not in the discontinuity, but rather in the fact that its domain is the set of real numbers. There are no difficulties in constructing a discontinuous function from the rationals to R. In particular, isPos is really straightforward to define, assuming rational numbers are encoded as a ratio of integers where the denominator is positive. As promised, I owe an apology. My previous video suggested that the elementary proof of the intermediate value theorem gives an algorithm for solving equations of the form f of x equals 0, using a binary search. But as we've just seen, we can't binary search on a general real number. So, on top of all the lies and hoodwinking already prolific in that video, I also lied in the first half. Although I stress that the elegant proof does not come with an algorithm, neither proof is constructive. For this infraction, as a Canadian, I have to say, I'm sorry, eh? If you're still here, thank you for watching. On your way out, thank PH Science for calling me out on my blatant deception. If you like the video, some recent literature reviews suggest that there's a way for you to express this. If you Hey, what about when you said programmers have no idea how to do math? What about it?